Hi everyone, nice to see you all again. I hope you have watched several videos, several online lectures on the portfolio theory, especially the conceptual framework from Harry Markovich to William Sharp. So in today's video, today's recording, we are going to see the technical companion, especially how to draw the efficient frontier and also the line connecting the risk-free asset and the risky portfolios. Okay, so I'll go straight to my file, my Excel file. So we'll use an example, a hypothetical example where we have several stocks. Okay, so suppose we have 10 stocks taken randomly anywhere, and we see that I got the daily returns for several days. So these are daily returns for 10 stocks. So we assume that we could build whatever available portfolios or attainable sets of portfolios using the 10 stocks. Right. So as usual, the first step would be, to find the individual assets, returns, and risks. Right. So I will do it quickly here. So I just use the notation expected return. Okay, I'll use the historical method. So just do the averaging, the arithmetic averaging. I think when you watch my previous videos, you notice that there's a major difference between arithmetic and geometric averages. And of course, for the case of the capital market and like financial assets or financial markets, geometric return or geometric average would be more appropriate. But for the sake of brevity and example, we'll just use the arithmetic. Okay, so do the arithmetic averaging for all the 10 stocks. So suppose we only have 10 stocks as the components or the stock components in our portfolio. Okay, so to make our life easier, I will give the naming. Okay, I'll just do the naming here. Define name. Okay, I define the name as expected return or whatever name you want to name it. I will just use E_R. Okay, and then as usual, we have expected return, and of course we have risk, and you can use the standard deviation of the population. Yeah, this is a typical formula that we are using. Standard deviation of the time series. Okay, so the same thing here. Make our life easier, we'll define the name as risk. Or whatever you want to use, and whatever name you want to give. Okay, so we have expected return and risk. And for now, just pretend that we will, whatever weights or proportions of all the stocks. For now, I'll just assume that we have like 10% each. Okay. Okay, so later we can change it, and the optimization software optimization was that tool in Excel called Solver, will help us determine and estimate and determine the proper weights that we are going to see in a little while. So we'll just use give the name, maybe weight. Yeah, just weight. Okay. Okay, so we have got expected returns for all the stocks and risks of all the stocks and weights and their proportions of their weights. So now I want to make the variance and covariance matrix, variance and covariance matrix. So I'll use in Excel. I'll get the help from Excel. I use data here, data and data analysis. Okay, data analysis. I use covariance. Okay, and then my range would be everything here. Okay, including even the from the first row. So just include everything here. Okay, and then grouped by columns, labels in the first row. I have labels there. You notice that? See, I have labels. Then output range, I will ask the output to be positioned maybe here. Okay, yeah, you can position it anywhere. You can make a new worksheet or even new workbook if you want. Okay, so I get the variance and covariance matrix, right? So again, in this video, this is a technical companion to the other video, so I will not explain further like variance and covariance matrix that we need for the conceptual and theoretical explanation when we build the mean and variance model based on Markowitz, and then the single index model by William Sharp. Okay, so we have this one, but if you notice here, we have some. I hope you can imagine, right? We have the covariance and variance. So the variance of stock one and stock one is the covariance of stock one and stock one is the variance of stock one. I think we can see that, right? Because the covariance and stock between stock one and stock two would be the same as the covariance between stock 2 and stock 1. In Excel, they don't show it anymore. But this will be quite, we will need them, the blank spots there. That's why we have to do something with it. So we'll just do the trick, okay? I'll do the trick quickly here. I will do the transpose. See here, the matrix here, I do the transpose. So I'll do the spatial, paste spatial, do the transpose. Where's transpose? Where is it? Here. Okay, transpose. Okay, you see here. Now I get the transpose. It's like the mirror. Not the mirror, but from left to right. Okay, left. Yeah, you turn. Like you're turning a book, right? You turn. Remember your high school lesson, matrix transpose. So I will fill in. Fill in the blanks. I'll just copy and then I'll put it here. Again, I do the paste spatial again. Paste spatial. Now I will just paste the values and skip blanks. I paste values and skip blanks. So I get everything, see? So this is just a trick, okay? So, okay, we can delete everything here. We can delete. Okay. Yes, now we have variance and covariance matrix. Now we want to name it as well. Yeah, whatever name you want to give, I will just name whatever, maybe far, cofar. Okay, I name it, so it will make our life easier later. Okay, now we have what's it now? We have variance and covariance matrix. Now we can calculate the expected return on the portfolio. Okay, and also the risk of the portfolio. So we'll start from the expected return. So remember in Markowitz formula, we have, for example, we have so many stocks, right? So W, the weight of the ith squared, right, times the variance of the ith squared, and you sum together. That's the first part, and then the second part would involve the weights and then the covariance, right? So remember, we have many other videos that have explained that. So I will just go straight into the technicality here. So I just want you to imagine, right? If you have only 2 stocks, maybe 2 or 3 securities, you could write on Excel using the manual formula. Right? I could write it. I hope you could imagine whatever, maybe 2 stocks. I could write in Excel. It will be quite easy. So I will write equal right? The cell, right? So the weight one squared, the variance of the first, right? And then, so we still can do it manually if we have only like 2 or 3 stocks, or maybe maximum 4 or something. Maybe we have 3 stocks here. Okay, we have pairs, weight 1, weight 2, and then covariance of the first and the second, plus 2, weight 1, weight 3, covariance of covariance of 1 and 3, and then 2 W2, W3, covariance of the second and the third. So we still can write it this way, right? And then we find the square root of it, right? The square root of the variance would be the portfolio risk. But can you imagine if you have 10 stocks or 20 stocks or something like that, it would be quite dangerous. If you had something like this in Excel, most likely you have a lot of errors there. If you have errors, it might be inaccurate, or you may not get any result because of the error, right? Formula error or something like that. So we have to use the matrix. Again, this video is not about mathematics, not about mathematical statistics or something like that, because you will need the matrix. I think basic knowledge of matrix operations, but just go back to your text or visit Google again to find out, to try to recall or recollect your knowledge on matrix operations. So I will just go straight. So I'll do it quickly using the matrix in Excel. So I will do MULT, okay, and then remember the name, expected return. Now you can imagine, right? Our life is much easier because I just need to write something like this, right? ER, expected return, that we named it before, and then I do the transpose. Okay, transpose of our weight. So remember the weight up there, the weight, right? The weights. Okay, we name them weights. Okay, so we get, expected return on the portfolio. Okay, expected return on the portfolio, and we could calculate the risk of the portfolio quickly. Again, we have to use the matrix operations because it would be quite dangerous if we write it manually. We have 10 stocks here. Can you imagine? So 10 stocks require 45 pairs. Remember the logic there. If we have 10 stocks, we need 45 pairs. How can we write a 45 pairing in on Excel? That would be quite dangerous. There will be a lot of errors there. Okay, so what about the risk? So MU, and then MU again, then MU, okay, and the weight, okay, the weight of so the far. So remember far, the variance and covariance matrix, okay, and then we transpose the weight again. Weight that we named above. So remember the weight. Okay, okay, so we get what? Yeah, something. Okay, so we get expected return on the portfolio consisting of 10 stocks, assuming that we invest, we put 10% in each stock, right? In this story, okay, the early part of our story here. Okay, so we get expected return and risk. If you change anything, then automatically the results will change as well. We adjust to your new inputs or adjusted values or anything. Right? Okay, so what is the purpose of doing this? We want to draw the efficient frontier. We want to draw the efficient frontier. I hope you still remember from the previous video. If we have this plane, okay, we have this one is the portfolio risk, and the vertical axis is the expected return on the portfolio. So we could have whatever portfolios here, okay, many portfolios. We call it attainable sets, right? Attainable portfolio. Attainable portfolio, so the attainable set of portfolios. But the outer side or the we call it frontier. That's why we call it frontier. It's like border. We call it efficient frontier. Why we call it efficient frontier again? Because this line contains all efficient portfolios. Right. So every portfolio contained on the line or by the line are efficient portfolios. What's the meaning of an efficient portfolio? A portfolio that dominates other portfolios. So I'm not going to repeat that part. Okay, so efficient portfolios are those that dominate other portfolios. That's why the line is called efficient frontier. So this is our main target here. We are going to draw using Excel. So it is a thing that we have to calculate automatically, because we have many stocks. It's impossible to calculate by hands. So we need a software package like Excel at least, and have many other software packages that we can use or apply to draw the efficient frontier. Okay, I will continue. So to continue our process, we need the identity matrix. You still remember identity matrix is like one for all the values, right? So I will just use one here. This is identity matrix, okay? So one for all the components here, the stocks. Okay, now we have to start counting the certain value. Yeah, this is rather traditional method. I will still use the A and B, C and D, or whatever you want to call it. You can call it that X and Y and Z, or W, X, Y, Z, or A, B, C, D, or any name that we want. To make it easy, I will just use whatever, A, B, C, D, maybe A. So we need these inputs later when we draw it using the matrix operations. So how to get the A? Okay, so I will name it first. This is our identity matrix. So we can call it anything you want. One maybe. Okay, what is A? Okay, A, this is the matrix multiplication, right? So mu, so expected return. Remember expected return that we named it before, expected return, with the matrix inverse. So M inverse, the matrix inverse of the far cofar. Okay, and then transpose of the expected return. Okay, so we get it. I'll check once again. Cofar transpose. Right. Okay, so then the next one is B. Point B is same thing here. Multiplication, mu. Then remember the name, the identity matrix, right? One. We named it one, right? Then matrix inverse of far cofar. Okay. Transpose of the expected return up there. There's something wrong. I have to check. Check slowly here. Mu. Okay, mu, and one. My first far cofar transpose of. Okay, maybe you have to do the control shift enter. No, not right. Huh. Mu, then the rewrite it, make sure. Oh, okay, got it. So this should be M inverse. So we lost one word there. Far cofar. Okay, far cofar, and then transpose of expected return. Okay, so we get certain value there. And then C, or whatever you want to name it, CC, or just to make up by yourself. MU, same thing, matrix multiplication, and then identity matrix, and then M inverse Markov and transpose of 1. This time the transpose of 1 for the C. Okay. Okay, and then D. Okay. And as usual, it's better to name them, make our life easier. So define name, we call it A, maybe we call it B, I call it C, then the D. Yeah, D would be the A times C, right, minus B squared. A times C, or CC here in this example, minus B squared. So we get a certain value. And as usual, name it D. Okay. Okay, now we got the components or inputs that we need. Now we just need to compile them, and then later we'll use solver to solve the what's it the minimization process. Okay. Now I want, for example, I want to know the order, the order from risk and expected return on the portfolio. So what would be the least efficient portfolio? Of course, individual stocks. Agree, right? A portfolio means you have more than one asset. So if you have two assets, that would be the most simple form of a portfolio. So what would be the least efficient portfolios or least efficient assets would be the individual assets. So we'll just copy everything here. You see, risk. This is a risks of individual assets. I will just transpose it here. I just transpose, what's the name again? Risk. Okay. We get this, right? Okay, the transpose of risk. And then same thing here. I will just do the transpose of expected return. Okay, that we did above. That's the benefit of naming your variable. So we just type it, and okay, so we get from stocks 1 to 10, right? Okay. So now I want to know what's the worst case or the least efficient case, right? Maximum. Now, an asset with the highest risk, it should be the maximum value of this, right? You understand what I'm talking about? So this is the maximum risk. So among the 10 stocks, the individual assets, which one is having the highest risk? So 0.7, meaning this one, right? Stock number what? Number 4. I think, yeah, I guess stock number 4. So this the maximum value would be the risk of one of the individual assets, because again, the least efficient assets would be individual assets because they are not combined into a portfolio, right? Individual assets. What would be the expected return? The expected return we can use, again, make it easy. We remember the B and A, B, C, D that we did above. So this would be B divided by C, right? Plus 1 divided by C, multiplied by the square root of, now the square root of D multiplied by C, D multiplied by, so inside, okay, C, multiplied by your risk, okay, your risk squared. So risk squared, standard deviation squared is your variance, right? So once again, B divided by C plus 1 divided by C times the square root of B times C times the variance minus 1. Okay, so we get something here. Okay, so now it depends how many portfolios you want to draw on the line, on the efficient frontier. You could draw maybe 15 or whatever, 20, 30 or anything. For this example, we'll just use like 15 portfolios. Right? So we only have 10 stocks. Right? We have 10 stocks, but we want to draw like 15 portfolios on the efficient frontier. Okay, so we have you see here the maximum risk and maximum expected return. Okay. Now we can do the minimum, right? The minimum risk and minimum expected return as well. So we call it. Do you still remember what do you call it here? This is global minimum portfolio, global minimum variance portfolio. So this is what we are looking for using the Excel solver. Okay, so global minimum variance portfolio. So for to determine this one, the minimization process that we are going to use solver, then we have to make the proportion. Okay, so I have stocks 1 to 10. Right? I have 10 stocks. Okay, now essentially I'm asking, right, if I want to minimize this, you see the picture there, I want to minimize the variance of all possible portfolios, especially on the efficient frontier. What would be the proportions of these stocks? Right, that's my question, right? And it will be solved by Excel. It's impossible to calculate by hand, so we use the Excel. So I'm asking, if I want to minimize this, what would be the proportions of all the stocks there? But for now, just pretend to write anything, okay? That it will automatically change later, but we just write anything for now, okay? The easiest way would be just spread it equally, and then the total would be, of course, 100%. Okay, so for now, just do it this way. Now I will write the formula, okay? I'll write the formula, the matrix operations. So to estimate the minimum, again, the minimum risk, global minimum variance portfolio, it will be a function of, wait, I have to name this as well. So let me name it, what is it now? Because we already had a weight up there. Maybe this one, whatever, proportion maybe, proportion. Because we have the name weight before above there. Okay, so proportion. So the formula will be as usual, MU, right? MU, okay. MU, okay, MU, and then transpose of what is the name again? Proportion, I guess. Yeah, proportion. With what's that? Far and cofar, variance and covariance matrix above. You see here. Yeah, this one. Okay. Proportion, far, cofar, and then again with weight, but we name it proportion here. Right? Proportion, and then we find the square root of it. Okay, so transpose of proportion with far, cofar, then proportion, and the square root of it. Okay, so we got the minimum, the formula for it. But this is not the final result because we'll use the solver. But at least we have the formula there. Okay, and then what would be the formula for expected return at a global minimum variance portfolio point. What would be the expected return? This would be the annual of expected return and the weight, proportion. Right? We know the proportion here. Okay, so we get something here. Okay, now we'll solve it using solver. Okay, so the formula are there, but these are not the final results because we haven't solved the optimization. Right? The optimization in this case is minimization. So what's our target again? We want to know this global minimum variance portfolio. So obviously we want to know what should be the proportion of each stock to minimize this, right? To minimize the portfolio risk. Okay, that's why we call it global minimum variance portfolio. Okay, so we'll just put maybe here and then data, and then solver. Okay, data solver. Now it's asking what is your objective? Your objective is this, right? Okay, the minimum, the risk on or risk of the global minimum variance portfolio. Once again, this is the risk of the global minimum variance portfolio. So we put it, that's our objective. And then what is it? Maximization or minimization or what? Of a certain value. Of course, minimization. Right? We try to minimize the value of the risk, the portfolio risk. By changing which variable? This one, right? Okay. But because we have named it, that's the benefit of naming. Remember what's the name again? I think proportion. Yeah, you just write proportion. Okay. And then what would be the constraints? The constraints, very easy. So your money should be 100%. So money should be 100%, right? Okay. In a certain capital market, maybe in many capital markets in the world or stock markets in the world, you might not be allowed to do the short selling. So if you are not allowed to do the short selling, then you have the second constraint. What is it? The proportion. Remember, proportion is the name that we gave to from stocks 1 to 10. This should be equal or larger than 0. Okay. So this one holds for a capital market or stock market where short selling is not allowed. Right. So it should be positive. Right? You cannot. Short selling means you sell something that you don't have, meaning that you borrow from your broker or your dealer. You sell it right now with a promise that you'll buy it back someday. You pay it back with interest. But if this is not allowed, then the proportion should be higher than 0, or equal or larger than 0. But if the capital market doesn't have any constraint, then we don't need this one, right? So it depends on. So for this case, maybe I'll just assume that we don't need the short selling constraint. Okay, so we just solve it. So you solve it, and then okay, you see, they change automatically, right? So now you know what is the minimum global minimum variance portfolio. The risk is whatever is it, 0.8% with an expected return on 0.004. So this is 0.008. Right, the risk, and then the expected return is 0.004. Is it? Let's see again. Yeah, 0804. Yes, yeah, something like this, right? Okay, and you know the proportions that you should allocate with. How do we know it? Solver tells us, right? Solver tells us, so we don't calculate by hands. Okay, very easy. And now we can fill the blank now. You see, we got the maximum estimate. We got, so essentially we got here, right? The maximum estimate, and then the minimum estimate. So again, we got the maximum estimate and the minimum estimate. Now we just fill the blank. How to do it? Yeah, it's just mathematical logic. Like I can do it this way. Like this would be, let me think about it. Maybe the previous number minus the maximum value. But remember to log it, okay? Because we're going to copy it down there. So the previous number minus the maximum number minus the minimum amount. Have to lock it. Okay, minimum amount. Yeah. Okay. Let me check. Is it correct? 95. Yeah, correct. And then divide it by how many portfolios we want again? In this example, 15. So should be divided by the number of portfolios plus 1. So divided by 16. We want to have 15 portfolios on the graph, right, on the line, but it should be divided by number of portfolios plus 1. Okay, so we just do the copy paste. It's very easy. Okay. Okay, so we fill in the blank, and then for this one, we just copy and paste from this one. They are congruent. They are just equivalent, right? Equivalent one to the next. So I'll just make a copy and paste. Okay, now we got everything. Now you can draw it, right? We can draw it easily from the max to the global minimum variance portfolio. Just insert whatever, maybe scatter plot, right? The easiest one, scatter plot. Okay, see the picture there. I know the picture doesn't look nice because I'm not professional in, no, I mean, our scales are not good. You understand what I'm saying, right? So the scale should be maybe smaller, or the example should be better, but it should look like this, right? The nicer picture, like the, what's that, concave, right? Concave shape. So it should be concave like this. Okay. But yeah, at least you know how to, we can do it using Excel. That's my point. Right? We can do it using Excel. And in today's modern technology, information technology or something like that, it's quite very easy. Not only can we use Excel, but we can also use other software packages, right? Python or anything, right? Maybe even better, more advanced. Okay, so this is Markovitch, right? The mean and variance model ended with the efficient frontier. So Markovitch efficient frontier, the version of efficient frontier. So now we're going to continue. We'll continue with the next step. Then came, a decade after Markovitch. Then came William Sharp. I see the story in my videos again. I have several parts of the videos. So William Sharp published another seminal paper. After Markovitch published it in 1952, William Sharp published his seminal paper in 1964, and that was considered, the beginning of not necessarily a new era, but new development, right? Single index model, and to be more precise, he named it like capital market line, security market line, or the capital asset pricing model, or the CAPM. Okay, so we are going there. So what is the difference? Now, when William Sharp came with the single index model, things become more realistic. Remember, we have an efficient frontier. Right? We have an efficient frontier here. And now, according to William Sharp, now we have this is called what? Risky portfolios. Risky. We have many portfolios on the line, right? The efficient portfolios on the efficient frontier. They are risky. They are risky. See, they have like risks. They pose risk, but they also have expected, or they offer expected returns. On the other hand, in the real world, we have risk-free asset. We have risk-free asset, and again, as we discussed in our previous videos, risk-free asset, this is arguable. Most of the time, I think almost certainly we use the return provided by or offered by a government security. So we could argue that now a government or a central bank actually could go broke, and we have seen many cases in certain countries. The government went broke, and so did the central bank. But we could argue as well that government securities, especially the government or the central bank, have a lot of approaches or the quote unquote ammunitions. Okay, if they need quick money, right, they could sell assets. They could levy more taxes, right? They could sell whatever state-owned enterprises. They could even sell islands if they want, right? And the easiest but the most dangerous one is printing more money, right? But they could, right? That's my point. So we have risk-free asset, most likely represented or proxied by government security, right? Return offered by a government security. So we need to connect them, right? We need to connect the risk-free and the risky portfolios. Okay, so if you watch the videos again, I'm explaining that actually we could have many possibilities, but the best possibilities would be the one that maximizes the slope, right? For example, you have here line number 1, line number 2, line number 3, line number 4, okay, and so on. So we ask that between lines 1 and 2, which one is preferred? Of course, line number 2, right? The second line is better than line number 1. It's very easy to prove. You see here, with the same risk, the second line offers a higher expected return. So the second is definitely better than the first. What about between the third and the second? Of course, the third is better than the second. So you will choose the third, right? You prefer the third to the second one, right? So the third is better. Now the question is, what about the fourth? All right, the third and the fourth, which one is better? Then you will prefer the fourth. Unfortunately, it's unattainable. It's not achievable because you don't have the capability of doing that, right? So what is the highest tendency? It's this one, right? Line number 3. Line number 3, that is connecting the risk-free and the risky portfolios. What is a solution here? Maximizing the slope, right? The slope here, right? The highest slope is achieved at this point. So this is our target now, right? This is our target. What's the name? What's the name of this one? Market portfolio or optimum market portfolio. I think we can call it M. Optimum market portfolio. We'll see in subsequent sessions or modules. The definition of market portfolio, according to William Sharp, is quite abstract, because he's saying that a market portfolio or an optimal market portfolio is actually a portfolio consisting of all assets in the economy. So it's not really pragmatic and not really operational. So how to operationalize the definition of this? Usually we are using a stock index, right? We are using a stock index, S&P 500 on Nikkei or Kospi, right? Straits Times or any kind of indices in the world. So we use a stock index to represent the market portfolio. But actually, according to William Sharp, an optimal market portfolio should be a portfolio comprised of all assets in the economy. But again, it's not pragmatic, right? Not really operational in the real life. So I will draw again. So now we got the connecting line here. So this is the M. So now we have a new efficient frontier that looks like this. Okay, so we are going to determine this point, right? The M, the highest slope, right? The highest slope. Okay, we cannot go beyond this line because we have to borrow money. But if we can borrow money, then we can go beyond the M. But suffice it for now to imagine this way. Okay. So we are going to find the M, right, the optimum market portfolio. And this line is called CAL, capital allocation line, or another name of it. Another name for it is a capital market line. So capital allocation line or capital market line. Okay, so we'll do it in Excel. So we do it with Sharp, okay? And we want to determine the capital allocation line or capital market line. Okay, capital market line. And as usual, we want to know the risk, right? Risk and risk of the portfolio, of course, and expected return on the portfolio. Okay, now what would be maybe before we go to Excel, it's worth repeating a bit, okay? You see the line here? So according to the simple algebra here, so remember the simple algebra, y is equal a plus bx, okay? Okay, so what is a y here? It's expected return on portfolio, right? The y. And then a, what is the intercept? It's a risk-free, right? The a, right? The intercept. And then what is the b? B is the slope, right? Remember the slope? Slope is always dy dx, okay? The first derivation, like dy dx. So plus, now we need to name it first. So this is m. So we could name it risk of the market portfolio, right? The sigma m, right? Risk of the market portfolio, and this would be expected return on the market portfolio. Let's just use the typical names. What's that? Names of variable, right? So what is the dy? Dy would be here, the dy. So expected return on the market portfolio minus RF. See here, dy. Okay, and then what is the dx? Dx is here. So here, right? The dx would be risk of the market portfolio minus 0. Yeah, of course, 0, you don't need to write anything, right? 0 is 0. Oh, wait. Okay, this is the slope, right? So this is called the slope. What is another name for the slope? Sharpe ratio. This is the famous ratio name, Sharpe ratio. It bears the name of Sharpe, William Sharpe. Okay, then what is the x? Remember we still have x here, x. The x-axis, horizontal axis is the portfolio risk. Okay, so minus 0, we don't need to write it. Okay, so now with the capital allocation line, it would be very easy to draw now. I will start from the beginning point. The beginning point, what is the risk of the beginning point here? What is the risk? Of course, 0, right? Risk-free, right? So the risk would be 0. Right? And what would be the expected return? Expected return on the risk-free asset, yeah, would be here. Right? The risk-free itself, right? The risk-free rate is the, yeah. So have we named it? Maybe not yet. I think it's, oh, okay. We have not determined the RF. Okay, let's do it now. Let's say risk-free is, what is it? 3.5% per year. I'll just make it easy to imagine. 5% per year divided by 365, because this is daily. Remember, this is daily analysis. Right? So 5% per year. I know today the risk-free rate would be 3.5%. But yeah, just assume, for example, it's 5% divided by the number of days. Okay, so we get something here, and we rename it, right, to make it easy later. So risk-free, RF. RF. Okay, going back here, the beginning line, the RF line, what is the risk? 0. What is the expected return? Of course, is the RF. Okay, very easy. Okay. What about the ending line? So ending line, for the ending line, we need to determine the slope first. Okay, maybe more proper to do it this way. Okay, so beginning line, maybe do it now. Okay, so I need the slope, right? I need the slope. But for ending line, we can put in the formula first. Maybe it's okay. I'm thinking how to do it more systematically. Maybe I'll do the ending first. So ending line would be, somewhere, wherever you want to end up, right? Ending line, or here, or anywhere. So for maybe could be exactly, anywhere. Just imagine where's the ending line. What is the maximum risk? So the least efficient, again, the least efficient asset would be an individual asset having the highest risk. Okay, so remember we have it up there. Which one is it again? This one, I guess, right? Okay, or just use the connecting link. Okay, so I will find the least efficient asset is the one that has the highest risk, right? Individual asset with the highest risk. Okay, so this one. Okay, so what would be the expected return? So remember the formula there, the formula. Okay, so expected return on a portfolio should be, could be anywhere. So risk-free plus, what is it again? See the formula there. So expected return on the market. So we need to find it, right? This is not yet determined, right? But for now, just write down the formula, okay? This risk-free plus expected return on the market that we are going to determine minus RF, right? Divided by, see the formula again, divided by the market risk of the market portfolio. And then multiplied by the portfolio risk. Right, something like this. So we have to solve the, what's that, the optimum, right? The optimum portfolio. So, but we have the idea there, the beginning and then the ending. Now we need to solve the optimum, right? Optimum M, the M, right? The M portfolio. So what is it again? This would be here, right? To determine the M. Okay. So to determine the M, the optimal market portfolio, we need to know, like what we did previously with Markowitz. We need to know how many or how much proportion to be allocated in stocks 1, 2, and so forth. So we have 10 stocks. And we have 10 stocks. Okay. For now, we just write as we did before, just 10%, and the total would be what? 100 some. Okay. Okay, so we write down the formula first. What would be the formula for risk? So this would be mu as usual transport. Oh, we need the naming, okay, to make it easy. So what name now for this one? We have used weight, proportion. This one may be W or WS or anything. Yeah, W sharp. Okay, so the weight for the sharp case. So WS. Okay, so I'll write the formula again for the M. So again, we are determining the M, right? The point M. Then the formula would be the mu transpose of the weight with go far with the weight again. Actually, it's very similar to what we did above, but the naming was different. And square root of it, I find the square root of it. Oh, okay. Oh, I have to check. Wait. Okay, mu transpose WS the weight. Far go far WS to the power of half. Yeah, okay. So this is the optimum risk. The risk of this one, the risk of the market portfolio. And then what would be the expected return on the market portfolio? This would be very simple, mu of expected return. You remember expected return above the earlier part that we did with the weight, right? The new weight, right? The WS. Okay, so we get certain numbers, but this will change. This most likely will change when we do the optimization. Okay, so now we can go back here to find the ending. Okay, because we got the estimates for risk of the market and expected return on the market, the optimal market portfolio. Right? So go back here again now, RF plus. Now we have expected return on the market portfolio. Which one is it? Yeah, of course, this one. Right. Okay. Minus RF. Yep. Divided by the risk of the market portfolio. Yeah, this one. And then multiplied by the x-axis. The x-axis is this one, right? Portfolio risk. Portfolio risk. Okay, so we get certain amount, certain number that will change later because of the optimization, but we write it down. Okay, now we'll do the optimization. So we are asking, right? We are asking solver, what should be the proportions of all of these to maximize? What to maximize again? The slope. Right, the slope, right? Okay, to maximize the slope. So we need to tell solver, I want, tell me the proportions of all the stocks there, the proportions of my assets, if I want to maximize the slope, the Sharpe ratio. Okay, so write down the slope again. Slope, what is the slope? Slope would be dy dx. So this would be, what's that again? Expected return on the market. Which one is it? Expected return on the market. Where's market? Market, I have this one. Expected return on the market minus RF. Expected return on the market minus RF, right, divided by risk of the optimal market portfolio. Yeah, this one, right? Okay, so we need to maximize this one, right? So once again, we are asking solver, what should be the proportion of each asset here if I want to maximize this, the slope, right? The slope is the Sharpe ratio to maximize the slope. Okay, so I do the solver. Is it solver? Yeah. over. So what is the objective now? Objective would be, oh yeah, here, yes. So B116, yeah, that's correct. Now what is it? Now it's not minimization, but maximization. So we want to maximize the slope, the Sharpe ratio. By changing, what is it? I think the name, what's the new name of the proposal? WS. Okay. And then the constraint, the total amount of money should be 100%. Okay. And if you want to add the short selling constraint, it means that this should not be less than 0. So it should be equal or larger than 0. Right? Oh, crap. Oh, wait. Just repeat it. Okay, just repeat it here. So the objective would be, is it again here? We try to maximize it by changing the weight, the new weights here, and then the constraint would be. Just want to make sure. Is it correct? So the total amount of investment should be 100%. And if we don't have short selling constraint, then this would be sufficient. But if you want to add a short selling constraint, then each proportion should not be less than 0. So it should be at least 0. Okay? So equal or larger than 0 if you want the short selling constraint. But otherwise, just sufficient to do this. So solve it. Okay, so we got this, right? So automatically change, and everything automatically change. The slope will change. So we find the maximum value of the slope. So this is what the optimum here. It means that this is what 0.006 and 010. 0.06. So this would be 0.006. And this would be 010. Okay. To the optimization. Okay, then we can draw everything if we want. Yeah, copy everything again from above, because the risky portfolios don't change, right? If you notice, risky portfolios don't change, but now we have risk-free and the touching line, the tangency line. The tangency line between risk-free and the risky portfolios. That's the M, the optimum market portfolio. Okay, so we copy it somewhere. Maybe here. Now I have this one. So beginning and then end. Let me think how to draw it properly. So I have beginning, I have ending, I have the optimum. Or maybe I only need this. And the touching point, yeah, maybe here. Yeah, this one. Okay. So draw it here. Yeah, I'll just do the past spatial and values, okay, to make sure that they don't change anymore. Okay, so I just added this one, right, for the Sharpe, right, the risk-free, and then the connecting line, and then the optimum market portfolio. Okay. So let's see here how it looks like. Hopefully it's nice enough, but I'm not sure because we need a better scale, I think, for the picture. But yeah, see, not really nice, but I hope you understand the logic should be. Wait. Oh, yeah, the scale is too low. See here, right, the risk-free right? The risk-free is like 0.00 something, so it should be like, yeah, a bit above zero, right? But we cannot see it because it's so minuscule to see the number there. So the scaling is bad. So it's like we have some line like this, and the M is here, but you cannot see it properly because of the scale. And this is like daily. These are daily data, making them more difficult to see. You see, like here, for the risk-free, the risk is zero. So actually, we want to say something like this, right? The risk is zero, but the expected return is, yeah, maybe a little bit above zero. That's the problem, right? So yeah, it should look like this. Yeah, but the scale is not. Yeah, the scaling is not proper. Yeah, you can try also in your own example. Maybe use the monthly data or annual data. They may look better. Right? They may look better. Okay, but at least we do it technically using Excel. So in conclusion, actually, you can do any kind of portfolio formation and capital market line using your own data and file. And hope you still remember. Maybe I will end the video with the capital from capital allocation line to security market line. So I'll just redo it here. Okay, so capital market line or capital allocation line is for a portfolio analysis. So if you want to adapt the capital market line into like an individual security analysis, then we change it to security market line, right? Security market line. So we have to change the name. Capital market line again is for portfolio analysis, but security market line would be for individual. Yeah, I'll do it quickly because this has been discussed in the previous videos. Just do it quickly here. Okay, so we change it to individual assets for the case of an individual asset here. Okay, we read out all other things are similar, right? Expected return on the market and then the market risk. But remember from the explanation of the single index model or capital asset pricing model by William Sharp, if we have a new asset to be included in a relatively well diversified portfolio, then only its systematic risk should be taken into account. So only the systematic risk should be compensated, in other words, right? Meanwhile, the specific component or unsystematic risk will decline and even disappear, right? Will diminish and disappear because of the portfolio formation. So once again, if you have a new asset to be included in your portfolio, and let's say your portfolio is well diversified, relatively well diversified, so you only need to consider or take into account the new asset systematic risk, because its unsystematic risk or specific risk will diminish and finally disappear when it enters the portfolio. Okay, so now because of that, I don't need to use the total risk. So I only need the systematic risk, right? The systematic component or the beta. Right, so I changed all the name here. Now the market, this is what? Beta of the market. Okay, so I rewrite the algebra again. So now expected return on an individual asset. This is security market line, SML. What is the A? The intercept is RF. But what is the dy dx again? The dy is expected return on the market portfolio minus RF. And dx would be the beta of the market minus 0, right here. Okay, and then what is the x-axis? the x-axis is the beta of the individual asset. So I could erase the 0. There's nothing here. And what's the beta of the market again? Beta of the market is the relationship or the sensitivity of the market and the market itself. Of course, beta of the market is 1. Because market is the market itself. If I ask you, like, what is the relationship between the market and the market return and market return? It's 100%. Because market is the market itself. So the beta of the market would be 1. Then you get the famous equation, the capital asset pricing model, right? So risk-free plus expected return on the market portfolio minus RF multiplied by the beta of the asset. So this is called market risk premium. Okay. Market risk premium. And this is capital asset pricing model. I think you saw it a lot in the previous videos. So I hope this is clear enough as technical companion, so you can draw your own efficient frontier, efficient portfolios, and also the capital allocation line, right? In the for a continuation from Markovich to William Sharp. Yeah, thank you for tuning in, and see you in our next video. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.